Hello and good day. We are starting algebra today with CO38, which is solving a system of equations by graphing. This system of equations is how objectives 38, 39, and PO40 all start. Solving a system of equations. What changes is the method that we're going to use. And we're going to start by graphing. Okay. And so when I kind of prefaced Unit 5 here, I said that word system means more than one, right? We've solved equations like this before, just y equals 1/3 x plus 1. Someone give me an ordered pair, a solution to that equation. First one you can find. Ready, set, go. Yes. 3, 2. So 1/3 of 3 is 2 plus 1, or sorry, 1/3 of 3, yes, is 2 plus 1 would give us 3, I think. No, 1/3 of 1, I should start this recording over. 1/3 of 3 is 1 plus 1 gives us 2. You are correct. 3, 2 is a solution to 1/3 x plus 1, okay? But when we're looking for a solution to a system, we want to know, you got to be kidding me.
Wait, what? Did I actually get it?
You did.
Did I actually solve it?
You did.
Let's go. Let's actually go. Let's go.
Start the recording over.
Oh yeah, he did get it right.
Pressure's on 8RK yet again today. What I was going to say was that the key is with a system is that we want to come up with the ordered pair that's a solution to both equations. And what I was going to do was plug in 3, 2 into our second equation here and point out that -2 times 3 plus 8 does not equal +2. However, it turns out it does. Well, okay, fine. Okay, so, yeah. This is horrible. Okay, well, it's very unlikely that you are going to guess accurately the ordered pair on your very first time that works in both of them. So, what? Unbelievable. So what the solving a system of equation by graphing method is we are going to graph each of these equations on the coordinate plane. Okay, so let's start by graphing y equals 1/3 x plus 1. It's in slope-intercept form. We've graphed slope-intercept form before, right? We start with that y-intercept, 0, 1. And from that point, we move up 1 over 3. And that gives us our second point. Okay, we want to make these lines as accurate as possible. So I'm going to continue to go up 1 over 3, up 1 over 3, just to get a few more points. Okay, and I'm going to connect these with my line, and there we have it. And what I was going to say was that, you know, what is true about every ordered pair that's on that line right now? What do they all have in common? Caleb?
They all have the same slope.
They all the same slope, right? Because they're all part of the same line. What else? Which equation are they all solutions to? Blake? The first one, because that's what we just graphed, right? Every ordered pair on this line is going to work in y equals 1/3 x plus 1. Joey could have literally picked an infinite number of... Never mind. Okay? They're all going to work there. But what we're interested in is what's the ordered pair that is also going to work in the second equation. So when we graph that second equation, what are we going to be looking for? What is going to tell us the ordered pair that not only works in the first one, but also the second one? Blake? It is 3, 2, yes. Okay, but when we graph that second equation, how will we know it's 3, 2? They're going to intersect at that point, right? So I'm going to graph this second equation in red. This one, y equals -2x plus 8. We're going to start by plotting the y-intercept of 8. Remember, the y-axis is the vertical one, so make sure you put it in the right spot there. And our slope, negative 2 over 1, this is why it's really important to be accurate. I want to do negative 2 over 1, negative 2 over 1, and continue to do so until I hit the line. And as Blake said, because all of the green ordered pairs are a solution to the green equation, the first one, all of the red ordered pairs are a solution to the red equation, the second one. What we're looking for here is where these two equations intersect. That's going to be the single, the only ordered pair that exists that Joey guessed the first time. That's going to work in both equations. Okay? Any questions? Okay. So let's look at the second one here. Y equals 5/6 x minus 3 and y equals 3/2 x plus 1. Rather than guessing an ordered pair and seeing what happens, let's just go ahead and graph each of these. Okay? In green, we'll do y equals 5/6 x minus 3. We're going to start by plotting our y-intercept of negative 3. And we're going up 5 over 6. So 1, 2, 3, 4, 5 up the y-axis, 1, 2, 3, 4, 5, 6 on the x-axis. And there's our second point. Okay? I can't get a third point by going up and to the right. So what can I do instead? Instead of going up and to the right, how can I get a third point in my line here, James?
On the dot on the y-intercept, you just go back 6 and down 5.
Right. Going up and right is the same thing as going down and left. If I go down 5, 1, 2, 3, 4, 5 down, 1, 2, 3, 4, 5, 6 over, I can get a third point. Why that works is because the slope of positive 5 over positive 6 is the same as negative 5 over negative 6. Because a negative divided by a negative is a positive, right? So going up 5, right 6 is the same line as going down 5 and left 6. It's very rare that we go left, right? But we're doing it for a purpose here, okay? And that's to get a third point that doesn't fit by going further to the right. If you want to connect these points with a line, you certainly can, like we did in the first one. Another option is not to, okay? It kind of keeps the points more clear, more accurate. So now let's go ahead and graph y equals 3/2 x plus 1. Okay. Starting at positive 1 and going up 3 over 2, up 3 over 2, up 3 over 2. Uh-oh. What do I need to do here to find that point? Caleb?
Go to the left.
Down and left. Okay. So down 3 over 2, down 3 over 2, down 3 over 2, and there it is. Okay, the single ordered pair, the one ordered pair that works in both of them. And what does that end up being? Negative 6, no, not 3, 2. I think it's negative 6, negative 8. Okay. I'm sure you would have guessed that, Joey. No doubt. Right? But this method works really, really well when your equations are given to you in slope-intercept form. Right? It's really easy to graph an equation in slope-intercept form. Okay? And where these two equations cross shows the solution that will work in both. Questions so far? Everyone with me? Considering you're seeing it for the very first time ever? Okay? All right. Let's go down a little bit here. It's 10:17. Where do the lines on each coordinate plane intersect? What does that mean? Where the lines intersect, we have those marked up there. And what does it mean? Okay. What it means is this is the one solution to both equations. Okay, the one solution to both equations. Each equation individually has an infinite number of solutions because it's a line that can be graphed and lines go on forever. But we're looking for the one solution that is a solution to both. Okay. So defining a system of equations. A system of equations, multiple equations with multiple variables that have the same value. Right? In a system, the x and y variables, and when you get to algebra 2, you'll have x, y, and z, so you have three variables to solve for with three equations, which brings us to the introduction of the z-axis. Did you know that the coordinate plane can have a z-axis? Yeah, the z-axis is a three-dimensional coordinate plane. It goes straight through the board. So if we were to have a z-axis here, it'd be coming straight out the board, straight at you. Okay, but we're not there yet. That's algebra 2. Right? But a system is multiple equations with multiple variables, and those variables all have the same value, and that's what we're trying to find. Okay. So here, what is the solution? The system of equations to the right. Write the equation of each line and show the solution works in each. So identify the solution to this system. What is it? I'd love for more than one hand to be up in the air right now, or two, or three, or four, or five, or six, or seven. Miranda? 4, 3, right? Why she was able to say that's the solution is because that's where those two lines intersect, right? Every ordered pair on this line with a positive slope going up from left to right, okay? In fact, this is a good opportunity to go back to function notation here. Every point on the f of x line is a solution to that equation. Every point on the g of x line is a solution to that equation, but where they intersect is going to be the solution to both of them. And that's what we're trying to identify. So what is the equation of the f of x line? Y equals what? What is that equation in slope-intercept form? Identify the slope, identify the y-intercept. What do you come up with? Joe?
Y equals 3 over 2, 2 plus 2.
So that's the x-intercept. We want the y-intercept. Minus 3. Good. F of x or y equals 3 halves x minus 3. What is the, if we plug in that ordered pair, 4, 3. 3 equals 3 halves times 4 minus 3. That gives us 3 equals 6. 3 halves times 4 is 6 minus 3, which does check out, right? So we've proven that that ordered pair works in the f of x equation. What is the g of x equation? Drew?
Y equals negative 1/2 x plus 5.
Good. G of x or y equals negative 1/2 x plus 5. Plugging in that ordered pair 4, 3, we get 3 equals negative 1/2 times 4 plus 5. Negative half of 4 is negative 2. And negative 2 plus 5 does equal 3. That checks out as well. Okay? Yeah, but great opportunity to bring back. This is where really function notation comes in handy. Rather than me saying that line, the one that's going up from left to right, the starts on the, rather than me saying that, I just say f of x. And if it's labeled, you know exactly which equation, which line I'm referring to. Okay? Question so far? All right. So the next page, I believe, is just several opportunities for you to practice. We just have 4 of them here. Okay. And your job is going to be solve each system of equations by graphing. And so you do need to graph each of them. Okay, no guessing here. Actually graphing them, right? And then identify where that point is. We can do one of them together. Which one would you like to do? Last one? The third one? Let's try someone raising their hand. I'll call on that person. Gino. Okay, the third one. All right, so y equals negative 3/5 x minus 5. We will do this one in red. So we're going to plot our y-intercept point down at negative 5. And from that point, down 3, right 5. I can't get another point by going to the right. So what's the same as going down 3 and over 5? Remember I've said before, it doesn't matter in a fraction where that negative sign is. It means the same thing. Negative 3 over 5, down 3 over 5 is the same thing as going up 3 and left 5, which is the same thing as that sign just being out in front like it is in the equation. They all mean the same thing. So up 3, left 5 will give me some more points to work with here. Okay, there we have it. The second equation we'll do in green. And we're going to start at positive 2 and go down 2 over 1, which is our slope. Continue that trend. Looks like we didn't really have to go up to the left here because we're going to hit our point right there. Okay. Everyone see how I got that point circled in blue there? Graphing each equation, seeing where they intersect. That represents the one solution that works in both. That ordered pair looks to be 5, negative 8. The directions do say to show how you've checked your answer. So what you then do with this ordered pair is go back to each equation. You got space to do it here. Plug in negative 8 for y. Plug in 5 for x. And check it. Does it work? Negative 3/5 of 5 is negative 3. So negative 8 equals negative 3 minus 5. That checks out. Okay. You then take that same order pair, 5, negative 8, go to your second equation, plug negative 8 in for y. Negative 8 equals negative 2 times 5 plus 2. Negative 8 equals negative 10 plus 2. Yep, checks out. Okay. This is a very colorful objective. It's very rare I get to use all 4 colors here. So, yeah. You see why this is starting to be one of my favorite concepts to teach here? Like this is good stuff. This is good algebra stuff here. It's actual application, right? Anyone think of a and then we'll stop because I know it's almost lunchtime. Anyone think of a real life application of where systems of equations would be helpful? Perhaps even life-saving, Gino?
I mean, like, I don't know, like heart monitor, something like that.
Well, remember here we're following 2 different things. We want to see where they intersect, like what where that point is going to be. Maybe heart. I don't know enough about
Maybe like sales or something.
Sales, advertising, sure. If the red line here represents males and the green line here represents people aged 20 to 30, and your job is to market males aged 20 to 30, you want to market at that spot. Maybe this is like when they watch TV, when they watch the Food Network or something like that. Okay, and you want to hit that market, you want to advertise at that time. Just an example, right? You're going to hit both of them. Good. Adam, what are you going to say? How about air traffic controllers? If 2 planes are following that flight path, do you want this to happen?
Yes.
No, you don't. Okay? You would want to be able to predict where they would intersect each other and then tell one, change your elevation, take an alternate alternate route, something like that. Air traffic controllers, they've got more than two lines going across. They've got many at once, and they have to be able to predict where these are going to intersect, and let's make sure that doesn't happen, right? So those are two examples of application of this concept here. All right, so that's your homework. It is due tomorrow with gusto, folks. That's how you math.
Don't forget to like and